Okay, so thanks for coming, everybody. Today's seminar will be given by Sisi, and it's on quantum error correction and continuous symmetries.
Okay, thank you. So today I'm going to talk about quantum error correction with continuous symmetry, fundamental trade-offs, and case studies. So this is joint work with Ziwen Liu from Parameter Institute. And we just have our archive post yesterday. So this is the archive numbers. So yeah, so I'll start with some general motivation behind this work. So we know that quantum error correction is a tool to protect quantum information against noise. And it is, in many cases, desirable to have symmetries on error correcting code. So, for example, if a code respects a certain type of symmetry, we can call it covariant code. And the interface between error correction and symmetries could be widely applied in many different scenarios, like in fault-tolerant quantum computing, quantum reference frames, holographic quantum gravity, and many-body physics. But we know that the famous Easton-Kneel theorem basically states that quantum error correcting code cannot be exactly covariant with respect to a continuous symmetry group if we require that it can correct just local errors. So it is a very strong evidence that quantum error correction is incompatible with continuous symmetries. And recently, there's a lot of works, and in particular, many people from Caltech is working on how to quantify this kind of incompatibility. For example, there's this approximate Easton-Kneel theorem. Basically, derives some lower bounds of the QEC inaccuracy for like exactly covariant codes. So the motivation behind our work is that basically in these works, in this work, the symmetry is kind of almost assumed to be exact, but approximate symmetry is actually ubiquitous in many different scenarios. For example, in like fault-tolerant QEC, because we usually just consider exact error correcting code, but the symmetry is kind of approximate, and also in other physical scenarios, for example, in condensed matter system and high energy, is also desirable to consider like approximate symmetries, because like the exact symmetry is sometimes forbidden. So basically our goal is to find a general way to quantify the degree of approximate symmetry, and basically obtain useful trade-off relations between like error correction and these approximate symmetries. So here's the outline of my talk. So basically I first just going through the setting of this talk by defining some quantum error correcting measures and symmetry measures. And then I'm just going to talk about the main results of our work, which is a series of trade-off relations. So to be specific, I'm going to talk about 3 different types of trade-off relations and talk a little bit about the proof ideas and proof techniques from different fields like approximate error correction, quantum metrology, and quantum resource theory. And finally, I'm going to talk about some examples and applications. So there's going to be a lot of formulas in this talk, so please stop me anytime if you have any questions. So, okay, so here's the setting. Basically, we're considering this type of quantum channel language. So epsilon is the encoding channel, which is basically defines the error correcting code. And n is the noise. So basically we need to specify which kind of noise we are considering. And also we have this recovery channel for the error correction. So basically the accuracy of error correction is defined by the distance between this channel and this channel. And of course, after optimizing over this recovery channel. So we are also going to consider, this another aspect of this code, which is its approximate covariance. So basically, here we are just going to consider this U1 group symmetry. So basically, this US theta and UL theta is going to be representations of U1 group. And by S and L, I basically mean the physical system and the logical system. So so basically it is defined by the Hamiltonian operator for these two U1 representation. And basically the code is exactly covariant if these two diagram, if like these two lines is equal to each other. And the distance between these two is going to quantify the approximate covariance of this type of encoding. So here is the exact definition. So we are going to use the purified distance between quantum channels, and it is defined by the square root of 1 minus f squared, where f is the worst case fidelity. So f is fidelity, and this type of purified distance is actually a distance metric between two quantum channels, which satisfy like the data processing inequality and some kind of nice properties. So that's why we use this purified distance. So now we can define the accuracy inaccuracy as the purified distance between the identity on the logical system and this error correction procedure. And we are going to minimize this whole thing over the recovery channel. And also we can define the what we call global covariance violation, which is the distance between the distance between these two quantum channels, which the first one is we have this unitary revolution before the encoding, and the other one is we have this unitary revolution after the encoding. And note that it is global in the sense of group, not in the sense of like spatial geometry. So we must be clear that the global here basically means that we are going to maximize this whole thing over all theta, basically on the entire group. And we also have this local covariance violation, which is defined to be the derivative of this purified distance at the point theta equal to 0. And then we take the factor of 2 and the square root. So this is just for the simplicity of calculation. So basically this whole thing is equal to the square root of the quantum Fisher information of this quantum channel. So so basically the quantum Fisher information is a measure of how much information the parameter theta have on this quantum channel. So basically given a quantum channel, the larger the Fisher information is, the more sensitive it is to the parameter theta. So finally, there's also this charge conservation violation, which is defined by the difference between this logical Hamiltonian and the physical Hamiltonian with the dual of the encoding. And by this delta here, basically this delta denotes the difference between the largest and the smallest eigenvalue of this whole thing. Is just kind of equal to it's just some kind of like norm, but not exactly norm, but basically quantifies the strength of this operator, the difference between HL and this HL.
Sorry, I'm already lost, CC. How did we get to a Hamiltonian all of a sudden? Up until now, it was just channels.
Oh, sure. So you mean like from here?
Well, I just didn't know what you meant by H sub L and H sub S. What are they?
Oh, yeah, they are the generators of this.
Oh, okay, you're right. I missed this. Okay, I
Yeah,
see.
yeah. Okay.
Generators of the logical and physical rotations.
Yeah,
Okay.
yeah, exactly.
Thank you.
Mhm. So yeah, so basically you can also say that this HL and HS are the logical charge and the physical charge. So yeah, basically, and that's why this is called the charge conservation violation, because basically it's the maximum charge you can change after the encoding. So okay, so this is the quantifiers of this properties we want to study. And so now I'm just going to talk about the trade-off relations, basically the trade-off relations between the QC accuracy and this global and local covariance violations, and also this charge conservation violation. So before we do that, I'm just going to introduce the first important concept, which will help us derive the trade-off relations. So this concept is what we call charge fluctuation. So basically, yeah, I think there's typo here. So this should be the dual of epsilon. I forgot the dagger here. So basically, the charge fluctuation is the difference between these two quantities. The expectation value of this dual of HS on 0 and the dual of HS on 1. So 0 and 1 basically correspond to the largest and the smallest eigenvalue of HL. So it is the eigenstate of HL, and which correspond to the largest and smallest eigenvalues. And basically, it can be shown that when when the code is exactly error correcting, chi should be exactly 0. In very in the most general cases, and also when the code is like exactly covariance, the delta should be 0. Delta should be 0, and also chi should be like delta HL. So if we want to have a non-trivial generator, delta HL should be like non-zero. So basically, it is an indicator of the incompatibility between quantum error correction and covariance. So to be specific, when the code is exactly error correcting, if we write down the noise channel, it needs to satisfy the Cornell-Laflamme conditions. And so pi here basically means the projection onto the code word. So I'm assuming the encoding is isometric here. So then if we satisfy the Cornell-Laflamme condition, we also need another condition, which is the Hamiltonian in crossband condition. Basically, it says that the Hamiltonian could be written as a linear combination of this Ki dagger Kj terms. So Ki dagger Kj. So this is just the noise operators, and this is the Hamiltonian. So it is actually a quite general condition, because, for example, if this Ki Kj are like local terms, then this Hamiltonian is also covers all type of local Hamiltonians. So so if these two conditions are satisfied, basically one can show that the Hamiltonian also need to satisfy, like we project it onto the code subspace, then it's going to be proportional to the projector itself. So then we just plug it in here. We can see that chi needs to be 0 if the code is exactly error correcting. So that's the first part. And the second part is what happens if the code is exactly covariant. So basically, in that case, it can be shown that, again, I forgot the dagger here. So basically, the dual of this physical Hamiltonian should be equal to the logical Hamiltonian if the code is exactly covariant with some like constant offset. So and then you can see that the difference between these two is going to be the difference between like HL. So then it is exactly equal to the delta HL, which represents the difference between the largest and smallest eigenvalue of HL. So basically now, basically it indicates that we can derive some trade-off relation between epsilon and delta global, basically by connecting each of this quantity to the absolute value of chi and the distance between delta HL and chi. So now I'm just.
Are you planning to talk about some examples? It's
Oh
kind
yeah,
of
like
abstract. Okay.
yeah, but actually it's like in the end, basically like the second half of this talk. Yeah.
Okay.
So yeah, so basically like so now we have our first type of trade-off relation between error correction and global symmetry. And so it looks complicated, but I'm just going to, it's not important. I'm just going to like decompose this whole thing into like different parts. So basically, so this blue blocks basically represent the strength of HS and HL, which is basically the strength of the charge. And this red block basically is this delta G and epsilon, which is the things that we want to study. Like we want to get the trade-off relation between delta and epsilon. And the rest is just a function of the noise. So yeah, because for different noise, we would have different trade-off relations. So that's kind of necessary. And we also need to, so this whole thing is also a function of the HS, which is the physical Hamiltonian. And the yellow part, which doesn't appear yet, would be the charge fluctuation. So here comes the yellow part. Basically, in order to derive this whole thing, we just need two steps. The first step, as I said, is the relation between delta G and chi. And the second part is the relation between epsilon and chi. So just by combining these two, we can get this whole thing. So the first part is actually quite, so the derivation is tedious and it doesn't have much like new, yeah, it's tedious, but it doesn't use like much basically inspiring techniques. So I'm just going to skip the first part and focus on the second part. So yeah, so the second part actually can be derived using two different techniques. So that's why we have this minimum, because first by analyzing the derivation from the Cornell-Lamb condition, we can get yeah, we can get this basically the absolute value of chi is lower upper bounded by 2 times epsilon times some parameter j. And on the other hand, using techniques from quantum metrology, we can derive this different bound basically by replacing j with this thing. So that's why combining these two, we have this whole thing. Actually, it's easy to show that. So these two different bound, we don't have an exactly a superiority between them. So basically, that's why we do need to combine these two together. So is there any question at this point? Okay.
But if you want to send me
yeah, I don't. Yeah, I'm not sure if anyone is talking about. Yeah, I'll just go on. So, wait, is there anyone asking questions? I cannot hear exactly. Okay, so yeah, so first I'm just going to talk about this first part. So how to derive the relation between epsilon and chi from Cornell-Lamb conditions. So So basically the key is that we use the lemma from Benny and Orskov in 2010. So it basically says that if a channel if a noise is not exactly correctable but is approximately correctable, so we would have this Canella-Flam condition approximately satisfied. So the first part would have this constants Mij times the projection onto the code, and we will have this additional like approximate terms, and then we can bound this epsilon by like the square root of 1 minus f squared between some basically quantum channels defined using this m and m plus delta m. So the detail, I'm not going to talk about the detailed expression here, and then basically we just choose this Mij, because we can choose this Mij actually quite randomly. So we just choose that to be like the average between the expectation value on 0 and the expectation value on 1. So, and then we can just plug it in here and using some different tools from like inequalities, like information theoretic inequalities, and then we can get this bound. So basically this bound could be derived using this deviation from the Canella-Flam conditions. So on the other hand, this other bound could be derived using method from quantum metrology. So by method of quantum metrology, basically I mean that I'm going to consider the parameter estimation of this quantum channel. So again, this US theta is the physical Hamiltonian evolution, and this NS is the noise. And we're just going to consider the parameter estimation of this whole quantum channel. And okay, so this is the exact expression of F. It's too complicated, you don't need to remember that, but basically F is exactly equal to the regularized quantum Fisher information of this channel. So by regularized, I mean I'm taking the quantum information of single quantum channel, and then I calculate this the quantum Fisher information of this whole thing using n copies, and then I divide by n and then take n to infinity. So this is the so this is the definition of this F, and I also have this quantity B, which is basically can show that it is upper bounded by, it should be upper bounded by like the square root of 2 times delta HS. I forgot a constant factor here. But actually, we're trying to argue that this B is sometimes negligible, because actually you can show that when delta P is pretty small, this B is actually proportional to like delta HL, which in most cases is just a constant. And in our examples, B is also like kind of negligible. So so this is the exact basically this the explanation of this expression, but I haven't described like how to derive it, like how to connect chi with epsilon using quantum metrology. So so basically the idea is that we are going to find an encoding channel and a recovery channel, which is basically the concatenation of the original encoding and recovery channels with repetition code, such that we can compute this a lower bound of this channel after the encoding and recovery. So the trick is that after we use this repetition code, this new channel is going to be a dephasing channel, rotated dephasing channel, which is basically the traditional dephasing channel plus poly Z rotation. So so this expression actually looks complicated, but basically you could kind of hand-wavily interpret it as the square of the signal to noise ratio. So the signal is kind of at the absolute value of chi. So you can imagine that if you want to estimate some kind of parameter theta, and then the strength of the signal is kind of just the difference between like the gap of the spectrum of this whole Hamiltonian. So and you remember that the definition of chi is kind of the gap between like HS on the 0 0 code word and 1 code word. So that's why we can interpret this chi as the signal. And the noise is basically what we have after we do this error correction procedure. And so basically now the epsilon is going to be the noise rate of this dephasing channel. So that's why this basically that's why we have this regularized QFI equal to like the square of this chi between this of this chi over epsilon. So and now we are just going to use the monotonicity of the regularized QFI. Basically, the QFI of this channel after error correction is going to be smaller than the QFI of this original quantum channel. So, which gives us this F. So that's how we get this bound between epsilon and chi. Okay, so yeah, so now that's my explanation of the first type of inequality. And now I'm just going to talk about how to derive another type of inequality, which is based on another important concept which we call gate implementation error. So it's kind of similar to charge fluctuation, which basically can tell us like how why there's a trade-off between QEC accuracy and global covariance violation. So basically, yeah. So basically recall that the definition of QEC accuracy is the difference between this error correction procedure and the identity, and the difference between this basically the non-commutativity of this Hamiltonian evolution with the encoding is going to be used to define the global covariance violation. And we can sort of combine these two together, which give us this what we call the approximate gate implementation. Basically, we are trying to implement the logical Hamiltonian evolution. But what we have is this noisy channel with encoding and recovery. So we are going to define the difference between this logical Hamiltonian evolution and this noisy evolution with encoding and recovery using this gamma, which we call the gate implementation error. So we can see that it is sort of a combination of these two effects. So if we only have like approximate error correction, it doesn't guarantee we can have small gamma, and we must have like both of these two be small in order to guarantee a small gamma. So actually we can derive this inequality between gate implementation error and and the sum of this QEC inaccuracy and this global covariance violation. So basically now we are actually putting the global, basically putting the QEC and symmetry on the same footing by using this type of inequality. And okay, so is there any question here? Okay, so yeah, so now we're just going to state our second trade-off relation between QEC and global symmetry. So it actually looks quite simpler than the previous one. So basically it's just delta plus epsilon is lower bounded by delta HL over 4 times, the square root of 4 times F. And again, this red part is the part where we want to study the trade-off relations. And this green part is the just functions of HS and NS, which is the noise and the Hamiltonian. And the gate implication error is going to appear here. So basically now we're just going to divide this derivation into 2 parts. The first part is basically, again, using this inequality, which is epsilon plus delta is lower bounded by gamma. And also, we are going to use method from quantum metrology to derive a lower bound of gamma, which is exactly have this form. And also, by using tricks from quantum resource theory, we can sort of get a different type of trade-off relation based on the Troy purified distance. So recall that previously I defined the purified distance using the worst case fidelity. But now if we just don't use the worst case fidelity, we just use assume the input state is the maximally entangled state, we can have this Troy purified distance, which is kind of the average over input. And then we can derive a similar stuff just with a different, basically a different delta HL here and a different type of F here. But basically the form, the trade-off relation is kind of the similar. We will have basically the same procedure going on here, but instead we're going to derive this this bound here, the lower bound of gamma bar, using quantum resource theory. So yeah, now I'm just going to
Sorry,
talk about, yeah.
Could you say what's the significance of this taking this global covariance with the Choi purified distance?
Oh yeah, so basically for the first part, the input states, yeah, if you, so basically the input state of this encoding channel is going to be taken to be the worst case. So we're just going to find the worst input states to like find out the distance between these two channels. But if we take this Troy purified distance, we're actually going to so it's actually going to behave quite similar to the average input. So for example, if the input state is taken over randomly from hard measure, so actually it's kind of I think it's kind of important in practice because we don't really have the worst case input state. Yeah, so it's just the difference between like average case and worst case.
Okay, thanks.
Yeah, so yeah, so again, I'm just going to first talk about this quantum metrology method, which is how to relate this gamma with this delta HL over the square root of 4 times F. So again, we're going to use the same trick, basically the channel estimation of this channel and as theta, which is the noisy Hamiltonian evolution in the physical system. But we're going to use a different recovery channel. So now we're just going to find a different recovery channel because now we don't just care about the estimation of theta at the point theta equal to 0, because that's related to the charge fluctuation. But now we're going to just find a theta star such that the lower bound of this F is going to be delta HL square over like gamma square approximately. So we can sort of interpret this delta HL as the signal and gamma as the noise. So you can sort of see that it's kind of a different flavor from the previous one. So basically in the previous equation, we have this delta HL replaced by the charge fluctuation. And the charge fluctuation can actually be small, but epsilon can also be small. But now we have this gamma, which is larger than epsilon. And so basically both the denominator and the, no, sorry. Basically gamma is larger and delta HL is also larger. So that's why, yeah, you can derive a different but also useful trade-off relation. And now we just use the monotonicity of the regular QFI. To find out how to relate this QFI after the error correction and the QFI before the error correction. So that's the quantum metrology method. And in terms of the resource theory method, yeah, again, I'm just going to rephrase the results on the previous slide. So recall that we have this very long expression. It's actually just the variance of this Bell's this maximally entangled state on this logical Hamiltonian. And yeah, so also here we need an additional assumption in using this.
Sisi, could you say again what this has to do with resource theory?
Oh yeah, so basically the point is yeah, I'm just going to talk about it. So basically the point is if we just consider the recovery channel as a covariant channel. So basically the resource theory is taking all covariant channels as free channels. And if we assume the recovery channel is a covariant, which is basically free, then the QEC inaccuracy is actually not going to be epsilon. It's actually going to be like gamma, basically lower bounded by gamma. So yeah, so and then if we also have this additional constraint, we can just use the monotonicity of this basically this coherence measure in resource theory. So we have this coherence measure, which is always going to be smaller or at least equal to the original, the coherence of the original state if the channel is free. So so then after the recovery, the coherence measure is going to decrease. So basically, and using this kind of a different type of monotonicity, we can get kind of a trade-off relation between delta and epsilon. So okay, so basically, I'm just going to be a little bit more specific here. So the coherence measure here is FR. And it is actually RLD QFI. So it is not the traditional QFI, but it's a different type of QFI. And it satisfies this monotonicity condition. And this curly F here is basically the channel QFI of this noisy physical Hamiltonian evolution and S theta here. So yeah, so basically the trick is that if a state is very close to a pure state, then this RLD QFI has the property of is going to be extremely large, because if a state is exactly pure, the ILD QFI is going to be like infinity. So okay, I think there's something which is blocked here. So now here it is 1 minus this whole thing is smaller than gamma. So I think the smaller than gamma is kind of missed here. But basically, when gamma is extremely small, this whole thing is going to be extremely large, and the numerator here is going to be the variance of psi on the logical Hamiltonian. And then basically what we do is we just choose the rho here to be the state after the error correction procedure. So we can see that it's going to be close to a pure state, but actually it's not going to be exactly pure state because the error correction is not exactly down. So the error correction is not perfect. So rho is going to be close to a pure state, and it's going to be close to the pure state in terms of the distance gamma. And we'll just take the input to be the maximally entangled state, and then using this monotonicity, we can get this type of lower bound of gamma bar. So but again here we need an additional assumption that the noise commute with the Hamiltonian, but it's actually somehow satisfied by many important noise model. Okay, so yeah, okay, so now I've just talked about the first type of trade-off relation between quantum error correction and global symmetry. Now I'm just going to talk a little bit about local symmetry, but I'm not going to talk about how to prove it because it's actually quite similar to the previous technique, and so that's why I'm just not going to repeat the techniques here. So for the local covariance violation, what we get is for isometric encodings, we have this type of relation, but basically the summation between the local covariance and epsilon with some kind of coefficient is going to be lower bounded by delta HL. And actually for general encoding, we have this more complicated relation, but it's effectively the same, only with this J replaced by the square root of F plus some small terms. And for the charge conservation violation, we have very similar result. Actually, for isometric encoding, the result is exactly the same. But for the general encodings, we don't actually, we have this additional factor of B here. So the reason is that in order to prove the bound for charge conservation violation, basically what we do is to use the relation between the charge conservation violation and the charge fluctuation. So recall that for the charge fluctuation, we do have a bound with this additional factor of B here. So that's why we have this here. But for the local covariance violation, we don't actually need this. We can use a whole different type of quantum metrology technique to derive this relation. So basically you can see that delta local violation cannot be too small. It cannot be like 0 when the system size grows, because basically we can see that the scaling of this delta P and delta C is basically just approximately this delta HL, which is kind of like a constant. So okay, so now I'm just going to talk about the behavior of these bounds. So we have two trade-off relations for global symmetry and like two relations for different type of local symmetries. And okay, now I'm just going to consider different type of noise. So the first actually quite important type of noise is random local noise. So basically we are assuming that the noise happens randomly but locally on different subsystems. So we are considering a n-partized system, and this SL is basically the different systems, and we have like n different systems. So the noise channel is actually going to be like happens with equal probability on each system. So this is just for like simplicity. We can actually have different probability, that's okay. But now what happens is what's important is the scaling of the bound. So for n-partized system, delta HS, which is one local, should be scale with linearly with respect to n, and the delta HL is just a constant. So we have like n scaling here and 1 scaling here. And the other part, which is J, square root of F and B. So this whole thing is, they all just scale with the linear scaling. So that's why we can write down this whole thing as has a scaling, linear scaling with respect to n. So now we can see that the scaling of delta G, when epsilon is below a certain threshold, it's just going to be like 1. Yeah. So actually the scaling of delta G is actually going to be like the square 1 over square root of n. The reason is that I think I forgot a square on the denominator here. So that's the reason why it looks weird, but actually the denominator would have a square here. So yeah, so forgive me for this mistake, but basically you can see that for this type of random local noise, the first type of global symmetry relation is actually better than the second type of global symmetry relation, because the first one is going to give you the square root of n, but the second one is only going to give you 1 over n. So that's for the random local noise. And for the yeah, and also I didn't talk about this local symmetry part, but basically as I said, the lower bound of this delta is always going to be a constant, so it doesn't matter much which type of noise you have. The only thing important is the threshold of epsilon, which is just 1 over n. Okay, so now that's the first part, which is the random local noise. And I'm also going to talk about the independent noise, or like ID noise. Basically, now it just doesn't have like noise acting random locally on each system. We just have the noise, which is a tensor product of noise on each subsystem. And in that case, the situation is going to be different. So the J, if you remember, again, it's going to scale linearly. But F is going to actually, the square root of F is going to scale like the square root of N. So it's different from the previous case where we have just N. So F is going to be smaller. It's going to be changed from N to the square root of N. And B, which the upper bound is still N, so it doesn't matter. But so basically in the end, if we have this square root of N plus N, we will still get N, so that's not good. But actually, we are going to argue that in our examples, basically B all just have the scaling looks like the square root of N. So if that is the case, actually the second bound in the first type is actually going to perform better. Basically in both cases, the lower bound of delta is going to be like, still like 1 over the square root of N. But actually, the difference is that the first type of bound and second type of bound will have the same behavior. So both of them is going to have this type of 1 over the square root of N lower bound. And for the local symmetry part, actually, the change from the previous slide is that the lower bound of epsilon is going to be 1 over the square root of N instead of 1 over N. So basically the scaling of delta is the same, but the scaling of epsilon is going to be different. So epsilon could be actually larger if we have this ID noise. Basically that's a signature that ID noise is actually stronger than the random local noise because if you just expand this whole thing using like Taylor series or something, you can see that it's not like local noise anymore. So and I haven't talked about other type of noise, but if actually the noise is even more stronger than the independent noise, the behavior of the second bound is actually going to outperform the behavior of the first bound, because if you just take a look of the first bound and forgot about this green part, the scaling of the first bound is always going to be the square root of 1 over N. But the second part, the bound is actually going to be determined by the scaling of the QFI. And if the QFI is even smaller than square root of N, the second bound is going to be dominant. And yeah, so basically it shows that these two types of bound exhibit different scaling with respect to different noise model. Okay, so finally, I'm just going to talk about examples. So the first example is the modified thermodynamical. So it is a superposition between between decay state with different charge. So decay state is basically the eigenstate of the Pauli Z, one local Pauli Z operator, and which is symmetric. And yeah, so the superposition is governed by this parameter Q, which is between 0 and 1. So when Q is 0, the code is exactly the thermodynamic code, which is exactly covariant. But when Q is 0, it is exactly error correcting. So basically, by going from Q to 0, from 0, Q equal to 0 to Q equal to 1, we can actually have a smooth transition from the exactly covariant code to exactly error correcting code against random local evasion noise. And you can actually calculate these type of quantities with different scalings. And yeah, I'm just going to show the plot here. So basically, if Q goes from 0 to 1, epsilon is going to decrease, and the other delta, different type of delta, is all going to increase. And you can actually look at the slope here. So you can see that the scaling of delta is going to be square root of 1 over N, and for local covariance, it's going to be like square root of n, and for charge, it's going to be a constant. So we can see that for the first, second, and fourth line, the scaling actually matches its lower bound, but there's a gap between the square root of n with this lower bound of delta p. So that's the first message from this modified thermodynamic code. We can also study quantum Reed-Muller code, which is, we're just taking the simple like two-dimensional code with distance 3. And we can just write down the code word, and it's basically the superposition between different shortened Reed-Muller code. And I'm not going to go to the details here, but basically it exactly corrects random local erasure noise. And we can also calculate these quantities, which again exhibit very similar behavior as the modified thermodynamic code when Q equals to 1. So the global symmetry have exactly the same scaling, but with a different coefficient. The local covariance violation is actually doesn't match its lower bound. And the charge covariance violation actually exactly matches this lower bound up to the first order. So and this is the last part of this talk. I'm going to talk about one application, which is how to use our theorems to derive the limitation on transversal logical gates. So if we consider exact error correcting code, we can just take epsilon to be 0. We will directly get some lower bound of delta G. And then actually delta G could be linked to the limitation of transversal logical gates. So now this is the first result. Basically, if we have a transversal implementation of a logical gate, and we assume that for the transversal implementation, the local Hamiltonians are just HSL divided by some D. And the logical gate is also HL divided by some D. And if we just assume like everything have like integer, so if H have integer eigenvalues, and in the end, we can prove that D is actually grows at most the scaling of n to the power of 3/2 when this HL and delta HSL are bounded. So basically, you can also grow exponentially with respect to n. And we can also use that to use this whole thing in terms of stabilizer code. So for stabilizer code, the transversal gate actually have this general form, which is the we have this kind of operator transversal gate here, and we also have transversal Clifford gates before and after this, and this is the Pauli operator. And basically, again, we can show that D grows at most polynomially. Basically, it means that it actually goes to at most the log n level of the Clifford hierarchy when this A is sort of controlled, when this A is like polynomial with respect to n. So to conclude here, we derive a series of trade-off relations between error correction and continuous symmetry based on different measures of symmetry, using various techniques from approximate error correction, metrology, and resource theory. And we also show two examples where the bound for global symmetry and the charge conservation is saturated up to the leading order. And in terms of fault-tolerant quantum computing, we demonstrate that limitations on transversal logical gates could be derived. So there are also some open questions. First of all, the two bounds on local covariance actually exhibit different scalings under different noise. So it would be interesting to find a way to unify them. And also there's this gap between delta point or local covariance violation with its lower bound. And also it would be interesting to explore the potential physical application of this trade-off between approximate symmetry and QEC, for example, in quantum gravity and many-body physics. Okay, so that's all. Thank you.
you talked about U1. Do you also have results for other groups like SUN?
Yeah, no, but yeah, we expect that it could be generalized to other groups by just using some, because for other groups you can just take some take one generator, because if the if the symmetry is respect to, for example, like SUD, it definitely is going to have the U1 symmetry as well. So you can just take one generator from the SUD and derive some bound. But actually we didn't work that out. So yeah, but we would expect it would have like kind of similar behavior as the bound for U1. Yeah.
It wasn't obvious to me how those limitations on transversal gates at the end were related to the other results. So in that case, you were talking about discrete rotations, right? By some.
Yeah. So
angle.
basically,
And I guess the conclusion was that, you know, the angles you could do, well, yeah, like what it says here, were getting smaller only inverse polynomially in N.
Yeah. So basically, but basically, even if it is this, so that's the reason why we need to study approximate covariance, because if D is too large, you can show that this code is going to have a very small delta. So yeah, because if it is continuous, then delta is going to be 0. But if it is discrete, delta is going to be small. So we can sort of show that. So basically, D cannot be too large, because delta actually have a polynomial lower bound with respect to N. So that's pretty much what's going on here. Yeah.
Okay, thanks.
So I'm not too familiar with I guess this covariant error correction. Do you have any intuition for why there's sort of this trade-off between covariance and error correcting capability?
Oh yeah, so yeah, let me just maybe go to the first few slides. So yeah, so the intuition is kind of like this. So basically, if error correcting works, you need to satisfy this Kinnear-Laflamme condition, and then basically the Hamiltonian is also going to be corrected as an error. So basically, if the Hamiltonian is kind of one local, it basically means that basically if you just do this error correction on the covariant code, then the Hamiltonian is also going to be corrected. So you don't actually have any type of covariant dynamic on the code.
Oh, I see.
Yeah.
Thanks.
Mm-hmm.
Well then, if there are no further questions, thanks for the talk, Sisi.